gained a carbon somehow. Well, all of your carbohydrates in your body come in the form of long carbon chains. In fact, that's what a carbohydrate means. It is a one carbon molecule that has one water molecule attached. It's a carbon that has been hydrated. In the case of like glucose, blood sugar, it's a 6 carbon molecule, right? In terms of fat, which are the only two places you're going to get most of your cellular energy, carbohydrates and fat, that is also a big, long block and chain of carbons. So whether you're getting your energy from fat or carbohydrate, you're going to split those atoms. So in other words, you've got 6 carbons attached to each other. And in this part of chemistry, it's exergonic. So when you break that carbon bond, so break one of those carbons off from the other, that's going to release energy. Just like if you had a pencil in here and I snapped it, you go bang and pop. I broke the bonds that were connecting that graphite to the next piece of graphite, and that released energy because I put energy into the system, etc. Okay. As a result, though, we've now had, say 5 or 6 carbons chained together. We broke one off the end, which is not how it works, but making the point. And now you have one free-floating carbon. You use that energy release to then go make ATP, to then go make your muscles contract. But now you've got carbon floating around. You can associate free-floating carbon with being at a higher acidic level. It's not going to happen. The only way that you're going to go through this process is if your body says, do we have an oxygen molecule available that we can bind this to immediately? Yes, we do. That carbon attaches to that oxygen molecule. You can't just put CO2 in the blood because of what we just talked about. So you're going to bind it through this bicarbonate process. It's going to go through your blood. It's going to go into the lungs. It's going to go back into its carbon dioxide molecule. It's going to go through the alveoli into the lungs, and you're going to exhale. So you went from carbon to this bicarbonate system, back into carbon, exhale. So inhaled O2. Plants go the opposite, by the way. So they're going to breathe in the CO2. They're going to cleave off that carbon, stack those carbons together, and that.
We metabolize carbohydrates and fats, produce carbon dioxide, and much of that carbon dioxide is transported in the blood through the bicarbonate system. Carbon dioxide and bicarbonate aren't two unrelated things. They're chemically connected through one of the most important buffering systems in human physiology. CO2 plus H2O can come from carbonic acid, which can dissociate into hydrogen ions, and bicarbonate. And that reaction is reversible. That's incredibly important because when arteries take sodium bicarbonate, they deliberately manipulate one component of this same acid-base system. They're increasing extracellular bicarbonate to give themselves additional buffering capacity during intense exercise. So baking soda works precisely because buffering matters.